everyone, welcome to today's video on describing and sketching functions. So when we're looking at graphs of functions, we want to be able to talk about them, describe what's happening, and then go from a word problem that's like describing a function to a sketch of it. You know, we're not necessarily getting all the details, but we can get a good representation of what's happening. So we're going to do one example of each today and then one you try. So for some important vocabulary, when we're going to describe functions and eventually sketch them as well, we're going to need to continue to remember the vocabulary of linear and nonlinear, which we've been doing for a while, right? In graph form, a linear function is going to be a straight line. When we're looking at these graphs of functions today, as you can see over here, it's going to be made up of lots of different pieces. Often, those are called different intervals. So the interval of time, this is one interval when the x value is going between -5 and -2. We see there's the same sort of thing happening there. That's one interval. So we're describing for each interval, right? So it's possible if I look at this graph is not a linear function because it's not just a straight line. We couldn't write an equation in slope-intercept form for it. But if we split it up into each of the individual parts or intervals, we can tell that each of those are actually linear. Okay, so that's the word we're going to use to describe the intervals, and then nonlinear would mean that they're not straight, they're curved. And then additionally, we'll be thinking about the terms increasing, decreasing, and constant. So we have that a graph is increasing when it's going up or when like a linear section has a positive slope. These are increasing. They're going to be decreasing when the graph is going down when we read it from left to right, and when it's a line, it's going to have a negative slope. And then we say it will be constant if it's horizontal. We have a zero slope and it's just flat. All right, so let's take a look at an example. Here we have that the graph on the right shows the attendance at a baseball park from an hour before the game starts to an hour after the end of the game. Describe the attendance at the ballpark as a function of time. Okay, so when they're saying a function of time, that's telling us time is going to be our input or our x value, and then this attendance is going to be our output, the y value, which we can see on the graph. Okay, so what are the two variables whenever we're trying to describe or sketch functions? That's an important question to ask ourselves. In this, we can see they are both time, and they don't really give us details there. Maybe it's hours, but it's not necessary for sketching. Time, and then the attendance at the ballpark. So those are our two variables. Attendance is the output, y, and then the time is the input, x. Then we're asked to look at this graph. We see a graph of a function, and we want to talk about what's happening on each of the intervals so we can describe it very accurately. So first we're asked, in intervals 1 and 2, the function is blank. Okay, so let me take a look here. So for interval 1, that's here, and interval 2 here, so we're really just looking at this part of the graph. Is the function increasing, going up, decreasing, going down, or constant, staying flat for that part in blue? Yeah, it's going up, so this is increasing. Each of these sections show that the function is increasing at those intervals. With some more detail, we could get at a later point that 1 is increasing and then 2 is increasing at a faster rate, right? So in the word problem, people are probably like a few really early birds are starting to come in like early before the game. But then once we get like 20, 30 minutes before the game, lots of people are coming quickly. So the rate of the people that are coming is increasing faster. So the line in 2, the segment in 2 would have like a higher slope. The steepness is higher, going up faster. Okay, but for the moment, really we need to focus on increasing. Okay, then let's take a look at 3 here. This is my interval 3. Is this increasing, going up, staying constant, staying flat, or is it decreasing, going down? Great, yep, staying constant, right? This is staying constant. It's flat, that line has a slope, or that section of the line has a slope of 0. Perfect. And then finally, interval 4. Is this increasing, going up, decreasing, going down, or staying flat, constant? Great. Yep, it's decreasing. We're going down. Awesome. Okay, so that's really all describing functions are. All of these components are linear intervals, right? Even though it's not overall a linear function, it's made up of parts of like lots of linear functions. And then finally, it asks us to describe the attendance at the ballpark as a function of time. So all they're saying there is they want us to take what we said in 2 and really talk about what that means. Okay, so as a function of time, we're talking about this x value, our function of time increasing, right? Time is passing, so time is going up. Okay, so we're going to say as time increases or like goes by, right? Because that's more what we say for time. As time increases or goes by, the attendance at the ballpark increases in intervals 1 and 2, stays constant at interval 3, and decreases at interval 4. So what does that mean, right? This probably means, if we're just imagining a baseball game, people are slowly coming in, then more people come in, then everyone's there. This is the baseball game. That's the game when it's staying flat. People aren't coming, they aren't going, people are watching the game. And then towards the end of the game and after the game, everyone goes home. Right? So it would make sense first people are increasing, then it's staying constant, and then it's going down. Awesome. All right, so let's have one you try here. You have a device that monitors the sound level of a conversation located 1 meter away. It's like 3 feet away. The results are shown in the graph. Fill in the blanks to describe the sound level as a function of time. Okay, so we have interval 1 here in blue. That's interval 1. Interval 2 here in red. And then interval 3 here in green. So you're just going to fill in for me as time increases, right? So as our time is passing. For the sound level, does it increase, decrease, or stay constant during interval 1, during interval 2, and during interval 3? Great, so in intervals 1 and 3, it's going up. This isn't a linear going up, but we see that it's going up. It's rising. And then in interval 2, it's going down. So it's decreasing. So there's not really any constant point here, or not like an extended constant point. We're just increasing, decreasing, and then increasing again. Okay, awesome. Finally, this is kind of working in the reverse way here when we want to sketch functions. We're given a word problem. We're given some information about what the situation is, what the graph looks like, and then we want to try to sketch a graph of it, right? It's not going to look perfect. It's not going to have all the detailed information, but just like this was for the baseball game or the sound level, it's a good description visually of what's going on. So in this situation, we have at sunrise, the temperature is 55 degrees. It rises steadily until noon. Okay, so we're starting at 55. It's rising steadily until noon. That was at sunrise. From noon till about 3 p.m., the temperature remains about the same. It slowly cools off after 3 p.m. The temperature then the temperature falls quickly after sunset. What does the graph of this function look like? Okay, so we have our input is time. You don't need to label this, right, if we're sketching, but I'm going to find this helpful because they kind of give us like 4 time checks. So I'm going to label them. I'm going to say the graph is starting at sunrise, and then we're at noon, and then it's 3 p.m., and then sunset. Okay, those are kind of the 3 time things, and we're just trying to describe what's happening to the temperature, right? At sunrise, we're at 55 degrees. Again, I don't really need to label it, but I think it would be helpful. We're starting at 55 degrees. It rises steadily until noon. Okay, so if it's rising steadily, that means it's increasing. Rises mean increase. And steadily here, that's a signal that this means it's linear. There's a constant rate of change, steady. Okay, so it's going to rise steadily until noon. We'll say that's noon. From noon until around 3 p.m., the temperature remains about the same. Okay, it's going to stay about the same until 3 p.m. It slowly cools off after 3 p.m. Okay, so we're saying it's kind of like slowly going down. So the slope there might be a little bit less steep. And then the temperature quickly falls after sunset. Okay, that one I might not make linear. I think I could or I couldn't. But then it looks like then it's quickly falling. Right, maybe not in a linear way. So we can connect those 4 intervals then back to the word problem just to make the connections. First, the temperature is 55 and it steadily rises until noon. Then the temperature remains about the same until 3 p.m. Then it cools off, so it's decreasing. And then it quickly decreases after sunset, right? Quickly dropping. Okay, so that would be a good estimate of what the graph looks like. So this is a sketch that represents the scenario. All right, that's all it is. Great job, everyone.